G'day. Today I'm going to have a go at explaining boomerangs, sort of like the aerodynamic archaeological design analysis way of looking at boomerangs, because I think more people should know how good they are and how they came to be the way that they are. Bugger the cultural cringe. Boomerangs are cool. When Captain Cook came to a place called Werrong, which is now known as Sydney, the people were hunting ducks and birds in the sky with a kind of a hardwood throwing knife, which were different sizes and variations on the theme. Although when Cook arrived at North Queensland, he found people were using four-bladed boomerangs made out of two sticks, and they were tied together at the hub using twine made from human hair. When white people came to make boomerangs, they had the advantage of a metals industry, so modern cross boomerangs use wing nuts. Perhaps, therefore, a lot of people delude themselves into thinking that the Aboriginal bent wooden boomerang is the more primitive version. The big problem with that theory is that the hubless asymmetric boomerang has a 60:1 glide ratio. The cross boomerang has a 40:1 glide ratio, and a six-bladed pinwheel from three sticks, it has a 20:1 glide ratio. Now, I'm not a big believer in backwards evolution, and as it looks, even 1, 2, 3, 4, 5 sheep out of 6 are interested enough to look at a boomerang, and if the cross boomerang doesn't fly as well as a one-piece boomerang, then that means that these are by far the more advanced design. So I posed myself the question, how does somebody who lives barefoot and naked on the floor of the forest and uses sharp rocks for tools come to make an auto-rotating rotary-wing sailplane in the first place? And the answer is by a process of design evolution. Here's how it works. Maybe 20,000 years ago, somebody gets a cylindrical section round stick and they throw it as hard as they can, underarm, straight up in the air, with the object of bashing into the birds that fly around up there. Now, sometimes it'd work and sometimes it wouldn't. But at some point, somebody got the genius of an idea of using a wedge to split the piece of timber. And that way, they could use twine to tie the two bits of wood together, flat side to flat side, and what they get is four ends to bash the birds with. You sweep the same disc and you've got the same weight, so you go more or less the same distance up into the sky. Turning this scenario into this one. In order to gain more altitude, the principle of add more lightness and simplicate means that you shave away everything that does not look like a flat-bottom, sharp-edged, symmetrical section, low-drag aerofoil. Once you've done that, suddenly some aerodynamic effects begin to kick in. It's not just pure ballistics and physics of rotation anymore. As the shape moves forward through the air, it deflects the slipstream down from the trailing edge and it generates a low pressure zone on top of it. And the low pressure zone is not symmetrical. It's angled forward, so it generates a low pressure zone in front of the leading edge. And because it's a cross and it's spinning, it has an advancing blade and it has a retreating blade. That's important. As the relative airspeed of the advancing blade is higher than that of the retreating blade, so the low pressure zone generated in front of the leading edge of the advancing blade is stronger and deeper. And this asymmetric low pressure zone actually spins the cross up until it becomes fast enough that aerodynamically it is a disc. If you build yourself a pair of aerofoils and strap them together flat side to flat side, and they're straight wings, then when you throw it straight up, it will auto-rotate, which means that it'll be spinning faster when it gets to the birds. However, it's going to fall straight back down, and when it impacts, it'll probably break. Take note that the only reason this arrangement will fly in a straight line even vertically is because the lift is balanced from the one side of the rotor to the other. If you try strapping the sticks together with the flat sides on the bottom, what happens is you generate aerodynamic lift and it starts flying in arcs all over the place, and that gets hard to control. Until somebody, probably by luck, worked out that you need to have a coning angle and make the tips of the disc higher than the hub. So now, like a helicopter rotor, it has a top and a bottom. And this coning angle, as it's moving forward through the air, generates lift off the leading edge of the disc. And if it hasn't got a tail, it'll promptly pitch through 90 degrees and change its direction of flight. And as it changes its direction of flight, it will roll through gyroscopic precession, so it'll change its orientation of flight. All of which meant you no longer had to lob the thing straight up, which is a fairly inefficient use of the human arms and its muscles. Instead, the idea is to take the boomerang and launch it like a frisbee, with its disc parallel to the horizon. So if you take one that weighs the same as a cricket ball, you can throw it as fast as a cricket ball. So your 6 or 7 ounce boomerang is going to leave your hand at 100 miles an hour or 160 kilometres an hour. It auto-rotates and becomes a disc. The disc pitches up through 90 degrees, gyroscopic precession rolls it through another 90 degrees, and it's purely ballistic. It increases its rotational speed, it slows down fractionally, it stores the energy as spin, so when it reaches where the birds may or may not be, it's spinning fast enough to break their wings. At apogee it then falls back down, increases speed, auto-rotates, becomes a disc again. It then pitches up, and as it pitches up, it rolls, so it then stores energy in the disc and it hovers for a landing. So if you miss the bird, you do not break your cross boomerang. Absolute work of genius. And you can make them more or less any size or weight if you can throw them. On the Queensland coast there were cross boomerangs that were 6 to 8 foot across and took 2 people to launch straight up into a flock of 1,000 ducks. You're bound to hit something. A cross boomerang can frighten a helicopter badly at 100 metres or 300 feet if it's the weight of a cricket ball. Right, so you got your head around the idea that the hunting boomerang can do a return shot if you use it vertically against birds in the sky. Then we have the phenomenon of the horizontal returning boomerang, which is basically a hunting boomerang that's been starved and it's so underweight that it can fly around the sky on a horizontal plane. The absolute limit for the disc loading of a returning boomerang is 2.24 ounces per square foot of swept disc area, or 223 grams per square metre. Anything over that and it's going to fall to the ground before it can return. If you're going for a target weight, try 1.97 ounces per square foot, or 175 grams per square metre. And that, in my opinion, gives you the ideal strength to weight ratio for the structure to form the free-flying disc. Now, in this diagram, the dotted lines show what happens when you throw the boomerang at 45 degrees across the face of a wind. Right? And the wind is going to be used to blow it back to you. If it's absolutely dead still air, it'll follow the hard dashed line. Okay, so you launch the thing at 80 to 85 degrees angle of bank, 30 miles an hour to 60 RPM, and as it goes out, when it auto-rotates and becomes a disc and pitches up, it'll turn left. Gyroscopic precession will roll it right, so it's now horizontal to the ground, maybe climbing a little bit, and it's increasing in altitude, but it's decreasing in rotary RPM. Eventually, it'll get to the point where it drops its nose and stalls, but gyroscopic precession will rotate that through 90 degrees, so it'll then dive down to the ground. As it dives, it'll turn speed into rotary RPM, and it'll lift its nose and flare for a landing. And the wind will bring it all the way back to you. The hubless, asymmetric, swept wing boomerang goes further than a cross boomerang, and the cross boomerang goes further than a 6-bladed pinwheel. Right? More or less any aeroplane freak will tell you that a swept wing makes less drag than a straight wing. So the hubless boomerang has swept leading and trailing edges, as well as less weight to sweep the same disc area. And it has less tip vortexes too. That's why it flies so much better. This is a little girl's boomerang in red cedar, painted by the probably 7-year-old at the time. This is a brother's in stringy bark. He painted his. He would have been 9 at the time. And this is a pair of identical research boomerangs, 2 of each, and they're right on the absolute weight limit for return boomerangs. The big ones are 7 ounces, the little ones are 3 ounces. The big ones are 2 foot diameter, so they're actually 3.142 square foot disc area. And the little ones are 17.2 inches diameter, so their disc area is 1.618 square feet. So they're Phi boomerangs. What I've done is I've paid attention to the direction of the chainsaw teeth marks so as to suppress or enhance the blade tip vortexes when flying, and it actually does produce a marked difference to the flight plan. Using the tooth marks and the grooves to suppress the tip vortexes, like this one, actually makes it fly further than when I set it up to enhance the tip vortexes. And the little Phi boomerangs, the one on the left has the tip vortexes neutral and the one on the right has them enhanced, and yeah, it has a pretty interesting difference to the flight plan there as well. Better to have it neutral than enhanced. And here's the cracker. The boomerangs can be safely flown in 20 miles an hour, that's 30 kilometres an hour. But the Chinese electric rechargeable toy helicopter can't cope with even 1/4 of a mile an hour. It has to have absolutely total dead still conditions. $100 when you buy it, so crash it at 10 seconds and it's $36,000 an hour. And I used it for 3 hours and 20 minutes before I got sick of it, and it was only $33.60. So let that be a lesson to you.